Welcome to the Deep Dive. Today, we are moving far beyond standard fire protection and really getting into some high-stakes precision engineering.
We really are.
We are tackling NFPA 15, the 2022 edition, standard for water spray, fixed systems for fire protection.
Yeah, and this is the code for, the really challenging, complex industrial environments. We're talking petrochemical plants, power generation, chemical processing, places where failure isn't just inconvenient.
No.
It's potentially catastrophic. So our mission today is to pull out those critical engineering parameters, the hydraulic details, the compliance hurdles, all the things that make NFPA 15 design just a completely different beast compared to, say, regular sprinkler installation.
That's a great way to put it, a different beast entirely. Because for our listeners, you engineers and learners living in this world, NFPA 13, that tells you how to protect an office building, right?
Right. Standard stuff.
But NFPA 15, this is about protecting a massive transformer or maybe a high-pressure vessel holding volatile materials. It shifts the whole focus. It's not just wetting down a fire.
Exactly. It's about achieving a specific calculated thermal result. Section 1.1.2, it demands these systems be custom designed for one of four very specific goals: fire control, extinguishment, prevention, or exposure protection.
Okay, so four distinct outcomes.
Four distinct outcomes. This isn't just generic coverage. It's like surgical application of water. And, right off the bat, we need to be clear about the professional mandate here. You'll see two key authorities mentioned throughout this standard.
The AHJ and the RPE.
Exactly.
Yeah.
The AHJ, the authority having jurisdiction, they enforce the code, and the RPE, the registered professional engineer, who ultimately, they're the ones carrying the responsibility for the design's integrity.
Okay, let's unpack the kinds of hazards NFPA 15 is actually designed for. Section 1.3.2 lays this out, and it really shows the scope of responsibility the engineer is taking on.
It does. The standard lists 5 critical categories for acceptable applications. First up, gaseous and liquid flammable materials. Think storage tanks, process lines, loading racks. Second, specialized electrical hazards. And this is where that precision spray becomes absolutely paramount, protecting huge oil-filled transformers, switchgear, motors, even extensive cable trays where the fire is fueled by insulating oil or just heavy electrical load.
Right, and spraying water onto electrical gear, that automatically raises the stakes, doesn't it? You need specific patterns, fast activation.
Absolutely. Non-conductive patterns are key. Third category, ordinary combustibles like wood or paper. But importantly, only in really high-hazard settings. Maybe conveyor belts running through volatile areas.
Not your average warehouse stack.
Definitely not. Fourth, certain hazardous solids. The standard specifically mentions things like propellants and pyrotechnics, high-energy materials where a fire could just escalate incredibly fast.
Take Cumbria.
And fifth, vapor mitigation. This might be the most technically challenging one, using water spray to handle invisible pre-ignition threats, managing vapor clouds.
Wow. Okay, when you list those out, flammable gas, huge transformers, explosives, the stakes are immediately clear. And NFPA basically warns the designer upfront in the disclaimers, right? They take no liability.
That's right. The responsibility falls squarely on the design firm and the RPE. Section 4.3 makes this official. It mandates that system design, layout, installation, it must be done by qualified persons.
And qualified means more than just having a certificate.
Oh, much more. Given the unique, sometimes experimental nature of the hazards NFPA 15 covers, the standard only provides the minimum requirements. The qualified person, the engineer, has to use independent professional judgment. They need proven competence and capability, as defined back in 3.3.18.
So it demands a deep understanding. The chemical process, structural loading, fluid dynamics, everything.
Absolutely. If you propose an alternative solution, or if you push the hydraulics near the limit, that RPE signature is basically proof that someone with the highest level of competence has looked at it and accepted the risk involved.
Okay, let's shift from the mandate to the actual mechanics, the hardware, the materials themselves. For systems handling high pressure, maybe operating in explosive atmospheres, surviving extreme heat, standard parts just won't cut it, right?
Not at all.
So what does NFPA 15 demand for pipe and fittings? Section 5.3.1.
We're looking at pretty strict standards here. The requirements point to various schedules of ferrous piping schedule 10, 30, 40 plus stainless steel pipe and copper tube. And crucially, these all reference specific ASME standards like B36.1 MEAM and B36.19 MEAM. That governs wall thickness, material quality.
Ensuring durability.
Exactly. Durability under both static pressure and the high dynamic pressures during activation.
But the standard does allow alternatives, right? Like lightweight steel pipe under 5.3.5. We know engineers often face pressure to cut costs or simplify things.
They do, but there are significant trade-offs the engineer absolutely has to account for if they go with, say, Schedule 10 or lightweight pipe instead of Schedule 40.
Okay, what are those trade-offs?
Well, the cost savings might look good initially, but Annex A.5.3.5 gives a serious warning. Lightweight steel pipe has a significantly reduced effective life compared to Schedule 40.
Why? Just thinner walls.
Thinner walls, exactly, which makes it much more vulnerable to corrosion over time, both internal and external.
So you save maybe 20% on the pipe today, but then it fails its 10-year internal check due to corrosion, and you're looking at massive replacement costs.
Precisely. And the engineering headache doesn't stop there. You also have to rigorously check the lightweight pipe's beam strength. That dictates your hanger spacing, your support needs. If you space hangers too far apart,
The pipe could sag.
it could sag. And even a slight sag could disrupt the precise trajectory of a spray nozzle. In a system designed for precision, that's potentially disastrous. The engineer has to consider movement vibration, temperature swings, and just the sheer dynamic shock when a massive deluge system kicks on. You have to ensure that movement doesn't compromise the structure or nozzle performance.
And the integrity of those pipes relies heavily on the joints connecting them. If the design uses welding, Section 5.5.2.5 adds a step that engineers may be only familiar with NFPA 13 might miss, this pre-installation qualification.
Yes, this is a critical difference from general practice. The welding procedure itself, not just the welder, must be prepared and qualified by the contractor or fabricator before any welding starts on site.
Hold on, why qualify the procedure before the project even kicks off?
Because the environment, the materials, the pipe thickness, the stresses an NFPA 15 system will face. They're unique. The RPE needs confidence that the weld produced by that specific procedure can handle the pressure and the potential cyclic loading.
So it's about guaranteeing the method meets the demand.
Exactly. It needs to meet or exceed standards like AWS B2.1 or ASME BPVC Section 9X. And there's specific requirements too. For circumferential butt joints, the code says the pipe has to be cut, beveled, and fitted so that full penetration is achievable.
Achievable. That word seems important.
It is. It's a practical distinction. It sets the goal for preparation without necessarily mandating extremely costly full penetration welding on every single pass, as long as the required mechanical strength is met.
Ah, okay. That clears up a common point of confusion defining the prep standard versus the outcome for every single weld. And what about slip-on flanges? Any non-negotiables for engineers specifying those?
Yes, Section 5.5.2.4.4 demands careful calculation of the throat weld thickness. It has to be at least 1.25 times the pipe wall thickness or the hub thickness, whichever is less.
A small detail, but crucial.
Absolutely crucial. That little measurement ensures the flange doesn't potentially separate under the shock load when the system activates. Even less common methods like brazing, they still need to comply with specific standards. NFPA 51B for hot work, AWS B2.2 for the procedure itself. Compromising a joint under pressure in these high-hazard areas is just not an option.
Okay, so materials and joints are solid. Now, structural support. For big pipes, NFPA 15 gets incredibly specific in tables 6.3.2.2.2, detailing maximum heights for pipe stands based on pipe diameter and support arm length. Why such fine detail on a simple stand?
It comes back to those dynamic loads. When a deluge system fires, you go from zero pressure to potentially hundreds of size almost instantly. That creates shock waves, thrust loads. If the pipe stands are too tall, they can be too flexible, or they might even buckle.
So the tables ensure rigidity.
Right. Rigidity to maintain the pipe slope, which we'll see is critical later, and prevent movement that could knock nozzles out of alignment, especially important when nozzle placement is calculated down to the millimeter.
This really moves beyond generic hanger rules into actual structural design territory. And if an engineer wants to attach piping directly to existing equipment like a pressure vessel or a big compressor skid, RPE certification becomes mandatory under 6.3.2.3. Why is that different from just hanging pipe from a building truss?
Because you're attaching a significant load, often a dynamic one, to something that wasn't originally designed for it. That vessel or equipment was designed for its process function, not to support a fire suppression system.
Right.
The RPE has to certify that the added load, the static weight of the pipe full of water, plus the dynamic forces when water flows won't compromise the primary function or the structural integrity of that vessel or equipment. Same idea if you tap or drill into load-bearing structural elements. RPE sign-off is required under 6.3.2.4 because you're permanently altering how that structure handles its loads.
Makes sense. And this structural thinking gets amplified in high hazard zones, leading to the explosion protection guidelines in 6.3.6. For places dealing with volatile stuff, how do you make sure the suppression system itself survives a blast?
Yeah, this is non-negotiable blast mitigation design. First, the system actuation valves, the main controls, have to be located remotely, at least 50 feet away, and they need to be housed in structures built to withstand significant overpressure.
How significant?
The standard specifies these structures must be blast resistant, designed for at least 3 psi static overpressure.
3 psi static. Okay, that's serious protection, designed so someone could still manually operate the system even after an initial event.
That's the idea. Protect the controls, protect the human interface. Also, piping to 12 inches or larger needs to be the welded flange type. This resists separation under blast shock much better than threaded or grooved joints. And Annex 8.6.3.6 advises engineers to physically shield the piping whenever possible. Route it behind structural steel, use existing columns as barriers.
Using the building itself as a shield against shrapnel or pressure waves.
Exactly. Protect that water delivery network at all costs.
All right, we've ensured the components are tough enough. Now, the next big step in the standard, defining the goal. How much water, precisely where, to meet the objective. Let's start with exposure protection for uninsulated vessels in 7.4 and that fundamental thermal load calculation.
Okay, the standard sets a minimum application rate, not less than 0.25 gallons per minute per square foot GPM FT-SART of the exposed surface area. That's 7.4.2.1. But, critically, NFPA 15 tells you why that number.
Ah, the assumption behind it.
Exactly. Annex 8.7.4.2 states, this rate is specifically calculated based on an assumed heat absorption rate of 20,000 B2 per hour per square foot.
That transparency is great, so the engineer knows exactly the heat load their system is designed against. If their analysis shows a worse fire scenario, potentially exceeding that 20,000 B2 rate,
then the standard forces them to use a higher water application density. They have to compensate.
and this rate isn't always 0.25, right? It changes for structural steel.
It does, based on orientation, which reflect the physics of how water runs off. Horizontal structural members think beams. They tend to hold water a bit better, less immediate runoff, so they require a lower rate, 0.10 GPM FT2.
Okay.
But vertical members, like columns, water sheds off them very quickly, so they need the full 0.25 GPM FT-SAR rate. That's 7.4.3.1 and 7.4.3.4.
That difference really highlights the specialization, doesn't it? Precision spray, not just flooding. But here's a potential game changer for cost and complexity. The alternative engineering analysis under 7.4.3.3 and 7.4.3.6. When can an RPE actually decide not to spray structural steel at all?
This is where the RPE really earns their keep, moving beyond just code compliance into performance-based design. They have to provide certified calculations proving the steel temperature won't exceed a critical level 1 that compromises structural integrity under the defined worst-case fire scenario. This requires some pretty sophisticated heat transfer modeling.
How complex are we talking? Is it a simple calculation?
No, definitely not simple. It's usually a transient heat transfer analysis. The engineer has to model the fire itself. How long will it burn? How severe is it? Is it a pool fire, jet fire? Then integrate the thermal properties of the steel, the structure's geometry, apply safety factors.
Well,
They need to figure out how fast the steel heats up versus how fast it loses strength. Often they're targeting a critical temperature around, say, 1,000 degrees Fahrenheit for typical carbon steel. It's complex, needs specialized software, deep thermo knowledge, but if successful.
you eliminate potentially a lot of pipe, nozzles, and water supply needed for those structures.
Exactly. Huge potential savings, but built on rigorous engineering justification.
That's a fantastic example of where that RPE judgment is required and potentially saves a lot of money.
Yeah.
Okay, let's shift gears to that fifth hazard category. Vapor mitigation, section 7.5. What's the goal here?
The main objective is using water spray to deal with a vapor cloud before it ignites. You want to dilute it, disperse it, or maybe absorb it to get the concentration below the lower flammable limit of the LFL. That's from 8.7.5. The whole strategy really depends on what chemical has been released.
How does it differ between, say, something water-soluble versus non-water-soluble?
Big difference. For water-soluble stuff like ammonia or alcohols, the water spray can actually absorb or dilute the chemical. The water acts like a sink, pulling the gas out of the air, or mixing with a liquid spill to lower its vapor pressure.
Okay, direct interaction.
Right. But for non-water soluble materials, think gasoline, propane, natural gas.
Yeah.
You can't absorb it. The water doesn't mix. So here, The water spray has to rely purely on dispersion.
Like using the spray as a big fan.
Essentially, yes. The high-velocity spray pattern acts as a massive mechanical air mover. It creates turbulence, stirs up air currents, and physically mixes the vapor cloud with fresh air to dilute it below the LFL.
So for those non-soluble cases, the spray density and pressure calculations aren't about cooling, they're about generating enough air movement. That's a different kind of fluid dynamics problem.
It absolutely is.
Yeah.
And this leads directly into the mandatory fire risk analysis required by 7.5.9. The 2022 edition made a really important update here. It explicitly forces the engineer to consider the potential for a vapor cloud explosion, or VCE.
A VCE, that's a major hazard.
Huge. And the risk analysis has to cover almost 20 different factors.
20 factors. Which ones usually end up being the trickiest design challenges?
Often, it's things related to business continuity, continuity of operations, and just understanding the physical properties of the chemicals involved.
Right.
Figuring out the probability and the potential scale of a VCE requires integrating complex models, gas dispersion, ignition sources, how confined the area is. But maybe the toughest part is predicting the cascading effects.
Like what else might happen?
Yeah, which systems might activate? How does that impact operations? Does the analysis show a need for explosion-proof electrical gear? How might blast pressure travel through the facility? That feeds back into the structural shielding we talked about earlier.
It forces the design to consider not just fire, but a potential blast, which happens much, much faster. Okay, final bit on design quantification. System sizing and simultaneous operation, 7.1.1.2. In these huge industrial sites, you can't possibly design for every water spray system running at once.
No, that would be massive overkill usually.
So how does the standard define the maximum required flow?
The design flow rate has to cover the largest logical combination of adjacent systems that could reasonably be involved in a single incident. You can't just assume only the system right above the fire source is enough.
Can you give an example? What's a logical combination that might surprise someone?
Okay, imagine 3 adjacent systems, A, B, and C. System A is over a heat exchanger, B is over a pump pad, C is over a cooling tower. A fire starts at the pump pad under System B.
Right.
Now, the burning liquid from the pump fire, B, could flow beneath A and C. At the same time, the heat and hot gases rising from B could easily trigger the heat detectors in both A and C.
Ah, so even though the fire started in B, the way the fire spreads, the liquid flow, the heat radiation, the hot gas movement, forces the engineer to calculate for all 3 systems, A, B, and C, running simultaneously.
Yes, exactly. A7.1.10 in year point 2 confirms this logic. You have to factor in burning liquid flow, hot gases setting off adjacent detectors, even the possibility of someone manually activating multiple systems from a control room. The engineer's job is to identify the single, credible, worst-case scenario based on fire dynamics and detection logic and design the water supply for that combined flow rate.
Okay, we've set the goals, figured out the worst-case flow rates. Now we get to the absolute core of the engineering. Chapter 8. Plans and hydraulic calculations. This is where the standard really demands rigor, separating maybe the experts from the novices.
It really does.
First off, hydraulic calculations are mandatory. You have to determine the required pressure and flow at every single nozzle. That's 8.1.1.
No skipping corners there.
Yeah.
And those nozzle pressures have minimums. For outdoor hazards where you've got wind, evaporation concerns, the minimum is 20 psi, about 1.4 bar. And Annex 8.8.1.2 wisely recommends bumping that up to 30 psi for small orifice nozzles, like 38-inch or less.
Why the higher pressure for small orifices?
You need that extra pressure head to really ensure the spray pattern forms correctly and maintains its shape against wind or other interferences. Get the water where it needs to go.
Makes sense. Now, let's tackle the big one. The cornerstone of complex NFPA 15 hydraulics, something often simplified or even ignored in less demanding systems. The velocity pressure correction, PV, that's 8.1.4. Why is PV so critical here, unlike in, say, most NFPA 13 sprinkler calcs?
The key difference is velocity. In standard sprinkler systems, NFPA 13, water velocity might hit maybe 15 feet per second, rarely much higher.
Yeah.
At those speeds, the kinetic energy component, the PV, is pretty small, often negligible.
Okay.
But NFPA 15 systems, they're designed for massive instant deluge. Velocities can easily jump to 30 feet per second, maybe even 40 feet per second near the main riser. At those high speeds, ignoring PV leads to potentially huge errors in your pressure calculations.
Can you break that down? If total pressure, PT, is all the energy available, what's PV doing mechanically?
Okay, think of PT as the total energy budget. PV is the portion of that energy budget needed just to keep the water in the pipe moving forward at high speed. It's kinetic energy.
Like the energy needed to keep a speeding train moving.
Exactly. Now, when a nozzle on the side of that pipe tries to discharge water, it can only use the pressure energy that's available to push sideways. That's the normal pressure, Pn.
Ah, so the equation is Pn equals PTPV. The pressure available at the nozzle is the total pressure minus the pressure being used just for forward motion.
Precisely. So if you ignore PV in your calculation, you're basically assuming all the total pressure, PT, is available to push water out the side nozzle, PPN. You're overestimating how much pressure is actually there to create the spray.
And that leads to undersized pipes or insufficient flow.
It can lead to insufficient flow at the nozzles, yes. NFPA 15 forces you to calculate and include PV unless it works out to be less than 5% of the total pressure at that specific junction point. It's 8.1.5. And Annex A.8.5.1.2 gives a stark warning. Ignore PV in high-velocity situations, and your final design might actually need over 26% more pressure at the source than you initially calculated just to get the required flow.
Wow, 26%. That's a massive potential failure in the design.
It's huge. And because PV depends on velocity, which depends on flow, which depends on the normal pressure PN, which in turn depends on PV.
It sounds like a circular calculation, a trial and error loop.
It is. Fundamentally, it's an iterative process. You estimate the flow, calculate the velocity and the resulting PV, use that PV to find the PN available at the nozzle, use that PN to recalculate the flow out of the nozzle, and then compare that flow to your initial estimate.
Can repeat until it converges.
Repeat until the estimated flow and calculated flow match within an acceptable tolerance. This level of calculation really necessitates specialized hydraulic software and very careful checking.
Okay. For the math itself, the standard points to the Hazen-Williams formula for friction loss in pipes, 8.5.1.1. Any specific rules about the C values used in that formula?
Yes, engineers have to use the C values from table 8.5.3.0 and use the correct one for the pipe material and condition. For example, new copper or stainless steel gets a C150 because it's very smooth inside.
Right.
But black steel pipe, which is common in wet systems, gets a more conservative C120. This accounts for slightly higher friction loss. The engineer can't just pick a higher C value to make their pressure numbers look better.
Got it. Stick to the table. Finally, the deliverable. The calculation package submitted to the AHJ. It's more than just a spreadsheet, right? What does 8.3.4 require?
The AHJ wants a comprehensive package. Yes, the detailed calculation worksheets, a summary sheet, but critically, a graph sheet. This graph has to be plotted on special semi-logarithmic paper using the Q1.85 scale for flow.
Q to the power of 1.85. Why that specific scale?
It relates directly to the Hazen-Williams formula. Plotting flow on that scale against pressure on a log scale effectively linearizes the system's pressure loss curve, making it easier to visualize. The graph must show two distinct curves: the water supply curve, what the pump or city main can actually deliver, and the system demand curve, what your calculations say the system needs.
And the AHJ looks at the intersection.
Exactly. That intersection point shows the expected operating point. The AHJ can immediately see if the supply curve is sufficiently above the demand curve, verifying that there's adequate pressure and flow with a safety margin. It's a crucial visual check.
We've wrestled with flow dynamics. Now let's add the ultimate constraint. Time. Extreme speed. We're moving into Chapter 12. Ultra-high-speed water spray systems, or UHS. This sounds like protection operating almost at the speed of reaction.
It really is.
What specific type of event are these UHS systems designed for?
UHS systems have a very narrow, specific purpose: the extinguishment or control of deflagrations. That's according to 12.1.1. A deflagration is rapid burning, but the fire front moves slower than the speed of sound.
Okay, slower than sound. So what are they explicitly not for? Section 12.1.2 mentions limitations.
Crucial limitations. First, they are not for detonations where the combustion wave is faster than sound. Water sprays simply can't react fast enough. Second, they can't be used to suppress deflagrations inside enclosed or confined vessels if the goal is just limiting pressure buildup. For that specific scenario, engineers need to look at NFPA 69, which covers explosion prevention systems.
So UHS is about stopping that fire front before it transitions into a full blast or detonation, or while it's still growing in an open area.
Exactly that. Intervening incredibly early, according to 12.1.3.
And the performance metric here is just astounding. Response time from detection to water actually flowing at the nozzle must be less than or equal to 100 milliseconds. That's 12.2.2.
100 milliseconds. Faster than you can blink. The system has to go from quiescent to fully discharging in literally a tenth of a second. And 12.2.3 notes that, depending on the specific hazard, even faster times might be required.
Wow. That single number, 100 milliseconds, must drive almost every design decision in Chapter 12.
It absolutely does. Let's look at some of those constraints. Start with system volume, 12.3.4. The capacity controlled by a single actuation valve has to be kept small, limited to 500 gallons. Why so small? Speed is inversely proportional to volume. It's basic physics, really. Annex A.12.3.4 explains that the time it takes to pressurize the pipes and fill them with water is a huge chunk of that total response time.
Inertia.
Inertia, exactly. The smaller the volume of pipework, the faster the water column can accelerate and reach that most remote nozzle. Trying to push, say, 5,000 gallons through a big network in 100 milliseconds. Hydraulically impossible.
Okay, makes sense. And the pressures required for UHS systems also reflect this need for speed.
They do. The minimum operating pressure at the most remote nozzle is significantly higher than standard systems. At least 50 psi, that's 3.4 bar, section 12.3.3.1. You need that high pressure for rapid water acceleration and also to guarantee the spray pattern forms perfectly, instantly for immediate cooling or dispersion.
And the density is higher too.
It's much higher. Minimum design density for area application is 0.50 GPMFT shore according to 12.3.2.3. That's double the standard rate we discussed for just structural exposure protection. You need a lot of water very fast.
Now here's an installation detail that sounds maybe minor, but in a millisecond world it must be critical. Pipe slope, 12.3.11.3.
But trapped air is the absolute enemy of UHS response time.
Why? What does trapped air do?
An air pocket acts like a spring. It has to be compressed before the water column behind it can really start moving.
Right.
That compression takes time, introducing an unacceptable delay into the system. So Section 12.3.1.3 mandates that all piping, even the small wet pilot lines that might trigger the system, must be sloped at a minimum of 1 inch per 10 feet toward a drain or vent.
1 inch per 10 feet, minimum.
Minimum, and you need air bleeder valves at all high points per 12.3.11.4 to get that air out. If that slope isn't maintained absolutely perfectly during installation or if air gets trapped, the 100 millisecond test will fail, period.
That's a level of installation precision far beyond standard sprinkler work. And with response time being everything, standard heat detectors are obviously too slow. What kind of sensors are needed?
You need fast-acting radiant energy sensors. Typically UV or IR flame detectors mentioned in 12.3.14.2. They detect the electromagnetic signature of a flame or spark almost instantaneously.
Okay.
And if the UHS system is also part of a vapor mitigation strategy, then the flammable gas detection system must also be installed and capable of activating the UHS system all by itself. That's from 7.5.7. So the deluge starts when gas concentration hits a certain percentage of the LFL, ideally well before any ignition happens.
Got it. Okay, finally, let's talk testing. Acceptance testing under 10.4.2 and 12.4. How does an engineer actually prove they met that seemingly impossible 100 millisecond target?
For UHS systems specifically, that 100 meters response time has to be verified during acceptance tests, as required by 12.4 and 12.2.2. The AHJ will typically require specialized instrumentation, high-speed timers, flow switches, to precisely measure the time from the detector signal to confirmed water flow at the designated remote nozzle.
Okay, direct measurement. But for all NFPA 15 systems, including standard speed ones, the acceptance discharge test in 10.4.3.2.3 includes a step that sounds, well, counterintuitive, the throttling test.
Oh yes, the throttling test. It is crucial, even if it sounds backward at first. During the discharge test, the main system control valve has to be partially closed, throttled down, until the pressure gauge reading at the hydraulically most remote nozzle exactly matches the minimum required nozzle pressure that came out of the engineer's hydraulic calculations.
Wait, you're deliberately reducing the system's performance during the test. Why on earth would you do that?
Because you're not testing maximum flow capacity here. You are testing the accuracy of the hydraulic calculation.
Validation.
Validation, exactly. If the system is running with exactly the calculated minimum pressure at the furthest point, then the total pressure you measure back at the riser, that's 10.4.3.2.3.1, must match, or be very close to, the total pressure the RPE calculated was needed at the source. This step validates every friction loss calculation, every elevation adjustment, and critically, those complex velocity pressure PV corrections.
So if the PV calculation was off...
If your PV calcs were wrong or pipe friction was miscalculated, the pressure reading at the riser won't match the predicted value when the remote nozzle pressure is correct. The system will either underperform or overperform relative to the hydraulic model, and the test fails. It forces complete accountability for the complexity we discussed in Chapter 8.
That is the ultimate proof of engineering due diligence, making sure the math matches reality under design conditions. And of course, documentation ties it all together.
Absolutely. The contractor's material and test certificate is mandatory, 10.1.2. This is the formal document certifying that the installed system complies with the approved plans. It passed the hydrostatic tests, the detection systems operate correctly within their required times, and importantly, it includes the results of that throttling pressure test. It's the official handover confirming the system is ready. #TagZV6. Outro.
Well, we have certainly covered a lot of ground in NFPA 15. We've
Mhm.
gone from the high-level mandates all the way down into millisecond response hydraulics. What are the absolute key takeaways for the engineers out there designing or reviewing these really high-stakes systems?
I think the biggest takeaway is that fundamental shift towards quantified specialized protection. NFPA 15 really demands precision engineering in, I'd say, three core areas.
Hmm.
First, certified judgment, especially needing that RPE sign-off for things like structural connections or alternative analyses.
Right.
Second, meticulous installation, validated by things like welding procedure qualifications and getting that piping slope absolutely perfect, especially for UHS. And third, mastering the complex fluid dynamics, particularly the non-negotiable accurate inclusion of the velocity pressure correction, PV, in every single calculation.
You just can't fudge the numbers or rely on big safety factors to cover sloppy hydraulic math when you're dealing with these kinds of deluge systems. That PV correction seems like the litmus test for a truly functional hydraulic model.
It really is. That rigor is what ensures that when these systems do activate, whether it's from a heat detector or maybe a 25 LFL gas alarm, they actually deliver the exact design density needed, whether that's 0.25 GPM FTA for cooling a vessel or that intense 0.50 GPM TMATO for UHS deflagration control.
And that focus on maximizing the water flow brings us nicely to our final provocative thought for you, our listener. As engineers are meticulously calculating how to get the most water flowing for fire suppression, Section 4.4.1 introduces a counterforce, runoff control.
Yeah, it's a critical constraint. The standard mandates that all that water being discharged has to be controlled or contained. You have to prevent it from spreading flammable liquids or other hazardous contaminants off-site. And in a big petrochemical plant, you could be flowing tens of thousands of gallons per minute.
Tens of thousands. And that water is now potentially heavily contaminated. Annex A.4.4.7 mentions that while maybe 4 hours is considered a practical maximum duration for sizing containment for a sustained fire, some major incidents can go on for 8 hours or even longer. The design challenge there seems immense.
It is. It forces the engineer into this balancing act.
Yeah.
You have the immediate need for massive water flow to save lives and equipment, right? But you have to balance that against the long-term ethical, environmental, and regulatory need to contain that potentially hazardous runoff. How do you integrate the hydraulic design from Chapter 7 with the civil engineering? The dikes, the trenches, the impounding basins needed to actually hold that total discharge volume, potentially for hours on end.
It's the final piece of the puzzle, isn't it? Solving the fire problem without inadvertently creating a major environmental or spill problem downstream. A crucial reminder that fire protection engineering never exists in a vacuum.
Well said. It always connects to the broader facility design and its environmental responsibilities.
Thank you for joining us for this deep dive into the demanding world of NFPA 15.
Always a pleasure to get into the critical details.